Hello, I'm Mehul Shah, the General Manager of the Amazon OpenSearch service. And today, I'll be telling you about all the great new features and capabilities we've added to the service and the dramatic changes that we've made to the service over the past year. I also have with me Wei Zhu from Pinterest, who will be telling you about their journey with OpenSearch as well. Before I get started, let me give you a quick overview of my talk. First, I'll give you some background on the Amazon OpenSearch service itself and the core open source product that it's based on, the OpenSearch project. Then I'll be diving deep into some of the great new features that we've added to make it easy for you to run OpenSearch at scale and cost effectively. Then I'll talk about the cutting edge features, capabilities, algorithms, and data structures, machine learning data structures that we've added and put into the open source software that you can use today. And finally, I'll go through what we have up and coming in the OpenSearch software as well as the service. And I'll pass it over to my friend, partner, and customer, Wei Zhu, to tell us about their journey. So the Amazon OpenSearch service is the successor to the Amazon Elasticsearch service. It's a managed service that makes it easy to deploy, operate, and scale OpenSearch and legacy Elasticsearch clusters on the AWS cloud. It's the same great service that you're used to, just a brand new name. What is OpenSearch? Well, OpenSearch is a search engine. Its name kind of gives it away. It allows you to do natural language queries or keyword queries over your documents that you store in OpenSearch. You can do Boolean queries, and you can also adjust the ranking of the results based on what your needs are. At the core of OpenSearch is Apache Lucene. Apache Lucene is an inverted index that makes it efficient to quickly find the documents that you need. And what OpenSearch does is it actually distributes Apache Lucene across a cluster of machines so you can scale your search engine to very, very large data set sizes. So in addition to text search, what we see our customers doing is also doing a lot of log analytics with OpenSearch. You see them processing a lot of streaming data, storing it at high volumes, and because it's a distributed engine, you can ask questions over it in near real time and get answers back in milliseconds. And because the engine distributes, you can also store a lot of data, so you get a lot of distributed storage. In addition to the engine itself, we have a visual interface called OpenSearch Dashboards that allows you to discover the data that you have in your engine, as well as do a number of different visual analytics over the time-based data that you have. So we have a bunch of time-based visualizations, you can do statistical queries, and we have a number of other time series tools that you can use. How do you use it? Well, you simply start with the data. You have data sitting in your servers, your applications, you have network logs, you have perhaps microservices that are running on AWS, and all of these things are actually generating tons and tons of data, what we call machine data. You might also have application data, for example, legal documents or Microsoft Word documents or social networking feeds and so on. And what you do is you take this, encode this data in a standard format called JSON, which is the interlingua for most machine data, and you send it to an OpenSearch cluster that's running on AWS in the service, the Amazon OpenSearch service. The data gets immediately indexed, and then it's instantly searchable. And OpenSearch is applicable to a variety of different personas for folks that are building applications or using applications, application users, data analysts and scientists, DevOps specialists, IT specialists, as well as security analysts. And there are a variety of different interfaces to kind of work with this data. You can run, you can ask questions directly using the REST APIs that are there. You can use some of the programming language specific clients that have been built and build applications on top. And then as a human, you can actually use OpenSearch dashboards and start browsing and visualizing the data that you have, and get into start trying to get some insights out of the data that you've stored. Here's what OpenSearch dashboards looks like. It allows you to, it gives you a number of different charting tools. You've got time-based line graphs, you've got stacked bar charts, and just a quick look at this, you can start seeing where some of the activity in your systems are. You can start drilling in and actually get to the individual log records, or you can actually roll back up and start moving around to see where there are problems or activity going on and find root causes of issues that you might have. You can also run ad hoc queries to just see what's going on with your systems. The Amazon OpenSearch service is run every day by many, many, many different customers that span the gamut, from small to medium enterprises to large enterprises, and a variety of different verticals: software and internet, social media, real estate, biotech, telecommunications, and so on. It's not restricted to a single vertical. And over the last year, we've been pretty busy. We've been building a ton of features for you. Since we last spoke to you in reInvent 2020, we've released over 50 significant features that you can use today in the managed service as well as the open source product. So what is the OpenSearch and the open source project? Well, many of you may be aware that in January of this year, the license for Elasticsearch and Kibana changed. After versions 7.10, these two pieces of software that are often used together are no longer open source. Now, we here at Amazon believe in open source. We believe in the way that it's built, we believe in the community, and we believe in the freedoms that it offers and affords our users and our customers. In particular, we believe in the freedom to be able to use it as they see fit, and the freedom to choose various vendors and deployment models as they see fit. Now, when we decide to build a service, we're ensure that we have the capabilities and are equipped to maintain it ourselves. And since so many of our users and customers depend on open source, we decided to fork Elasticsearch and change the name to OpenSearch, simply because Elasticsearch was no longer open. So OpenSearch consists of a number of different components. There's the OpenSearch engine itself, which is a derivation or a fork of Elasticsearch 7.10. A visual interface called OpenSearch Dashboards, which is a fork of Kibana 7.10. And it also includes a series of tools and plugins and extensions that we used to package together as part of Open Distro for Elasticsearch, our precursor to OpenSearch, but now it's part of the OpenSearch project. And these plugins give you enterprise-grade extensions like security, anomaly detection, machine learning, alerting, and so on and so forth. And we keep on innovating in this space. We're keeping on investing in this space. So why OpenSearch? Why should you use it? Well, first, it's community-driven. It's we are the steward of the project right now, but all the decisions that we make are in the open, and it's done with community's input. Okay. The roadmap that we have is public. You can actually see it on GitHub. And we take feedback in various forums online, through community meetings, through GitHub itself. And we welcome contributions from anyone that wants to participate. For example, today we already have co-maintainers that are helping us maintain popular language clients for OpenSearch itself. OpenSearch is 100% open source. It's got it uses the Apache version 2 license. And it's a license that we know in industry really well. You're allowed to use it, modify it, deploy it and run it anywhere you want to run it, monetize it. All of this stuff that we're doing, all of the innovations that we're putting in are built in the open. And we make it easy for you to contribute. In particular, for example, we don't have a contributor license agreement, which a lot of other open source, which sometimes you find in open source projects. It's also full featured. It's wire compatible with Elasticsearch 7.10, so you don't have to change your applications, and you get all of the great features that you see in Elasticsearch: full text search, analytics, fast ingest, machine learning, and we continue to add more to this project. So what does this mean for you? Well, it gives you a path forward. If you're an Elasticsearch user, you're not stuck on a particular version of Elasticsearch. You can move forward, keep on advancing and taking advantage of the great new features and functionality that we continue to put into the system. There's no lock-in. It's the same software that you had before that you're going to get from us, and you can run it anywhere you want, on premises, in any other cloud, or on our cloud. It's backward compatible, so because of the wired compatibility, you don't actually have to make any changes to your applications, including any language clients that you're using. You don't have to make any changes to those as well. And finally, we continue to innovate at the same pace that we're innovating before, adding in features that you've been asking for and you know and love. So just in the first few releases, we've added features like notebooks and data streams, bucket level alerting, and we continue to invest in this open source software. So with OpenSearch, the open source software, you can certainly manage it on your own, but with the Amazon OpenSearch service, it's actually a great home for all of your Elasticsearch and OpenSearch workloads. You don't have to manage it yourself. You can use the OpenSearch service to manage this manage your OpenSearch clusters. We remove all of the operational overhead for running your clusters, the undifferentiated heavy lifting of provisioning and patching and and fixes and so on, bug fixes and so on. We also provide comprehensive integrated security, for example, encryption in flight, and at rest, authentication, fine-grained authorization, and we have all the relevant compliances that you may be interested in, like HIPAA, PCI, SOC, FedRAMP. And of course, all of this comes to you and is provided by you by the stewards of the open source software. So, what better place to run your OpenSearch workloads? All right, now let's talk about some of the cool features that we've added to make it easier for you to scale your workloads in the cloud and make it cost efficient and manageable to run it. Before we get started, I think it's important to understand the architecture of OpenSearch. OpenSearch is a data parallel system. Okay, so what this means is you take your data, you chop it up, and you break it up across a collection or a cluster of nodes. In this case, we've called them the hot data nodes in the slide, and the data nodes is where all of the indexing is happening and all of the search requests and the computation happens. The leader nodes actually store the metadata for your cluster. So they store where your individual partitions or shards are. They store where the replicas of those shards are. And they also keep track of cluster state, which nodes are in the system, which ones are unhealthy and pulled out of the system. Now, the nice thing about this architecture is it's really easy to scale. If you want to, add more data or scale the compute, you just keep adding more and more nodes, and you get more compute and you get more storage with it, and you can do more with it. The drawback, and the system automatically kind of rebalances the data, across these nodes as you need. The drawback of this architecture is that as you add more and more data, because storage and compute are coupled, you have to pay for additional compute, even though you may or may not need that compute. And practically speaking, given that all the metadata is right now stored in the leader nodes, the biggest size cluster that you can run right now is a 3 petabyte cluster. All right, so about a year and a half ago, we introduced UltraWarm. UltraWarm is a new warm tier of storage. Okay, and what it allows you to do is take your older, less frequently accessed data and move it to a lower cost tier that's about 90% cheaper than the hot tier that we just talked about. And so this actually starts decoupling compute and storage for you. Now this tier is actually pulling in data that we've put on S3. So we take your indices, your shards, and we make them immutable, and we store them on S3. And this tier actually caches the relevant data from S3 as needed, and computes the queries as you need and returns the answers to you. Now this is fast enough, it turns out, to do most interactive log analytics and visualization. Now the maximum cluster size is still 3 petabytes because all the metadata is still managed by the leader node, but you can get a lot more cost efficiency because of UltraWarm. Asurion is a company with 350 million customers, and it offers phone and protection plans for phone and home tech devices. And they're using OpenSearch for all of their log analytics and their cloud operations. And for them, their most valuable data is really their most recent data. And the rest of it is also important, but they really needed to be able to go and take that data and reduce their overall cost. They put it in UltraWarm, and they were able to migrate seamlessly. They didn't have to change any of their dashboards, their existing workflow processes for creating new indices and rotating them out just worked naturally. And they were able to get this up and running very quickly. But there are some customers that came to us and said, hey, we just need more storage than 3 petabytes. And so this year, we launched cold storage in May of this year. And what we're doing with cold storage is we're allowing you to decouple your UltraWarm indices from the UltraWarm nodes into S3. You can detach them manually, or you can detach them using data lifecycle policies and automatically bring them out and bring them back in as well. So when you need to go and query some of these indices, you can reattach them again manually. You can discover them through our UI in OpenSearch dashboards, and then start working with that data again. But now with cold storage, the nice thing about this is that you can scale the amount of data basically ad infinitum in your OpenSearch clusters. Verizon is one of our customers that is using cold storage. And, like many other customers, they have different peak and lull periods in their organization. During high traffic times, for example, during iPhone launches or Black Friday sales, they often have to scale up their cluster and then they bring it down. And so they want to keep track of the history of their cluster and the history of the indices that they have over time. And so they've been able to go and take all of those all of the workloads that they've had and move them into cold storage so they can go back and do forensic analysis. And they've also been able to, not forensic, but research historical events. And they've also been able to retain much longer timeframes because of cold storage. Another cool feature that we have in the Amazon OpenSearch service is AutoTune. It's so now every new cluster that spins up is enabled with auto-tuning. So we all know that distributed systems can be quite complex, and that if they're tuned, if they're configured incorrectly, your performance is going to suffer. In some cases, it can actually grind to a halt. Now, even if you know how to tune your cluster, your workloads are always changing. The data that you're running is also changing, and the performance of your system definitely depends on the workload and the data. So having something that continuously monitors, learns, and adjusts the parameters to optimize cost and performance is necessary, especially at scale. And so we released AutoTune, and AutoTune works exactly as you would imagine. It actually has deep telemetry into your clusters. That telemetry is sent back to our control plane, where we make per node evaluations as well as cluster level evaluations to figure out what parameters to adjust to continue to have your clusters perform well. We make those changes, apply those optimizations, and then rinse and repeat. There are a number of different parameters that we tune currently: queue sizes, data cache sizes, the sizes of the heap in the Java virtual memory, as well as generational garbage collection. And we're adding more and more parameters that we can tune automatically. A financial service customer, actually came to us and told us that they were, ingesting billions of events a day, roughly 2 to 3 terabytes a day, and they were having trouble managing their indexing and query because there was a lot of garbage collection that was going on, and they were seeing a lot of JVM memory pressure. We turned on AutoTune for them. It automatically increased the bulk queue size by 5x, the search queue size by 2x, adjusted the heap to 128 gigabytes, and enabled generational garbage collection. The most important point is, after turning it on, JVM memory pressure dropped 90%, the throughput doubled, and their error rates went down to 0. So they were able to keep the same size cluster and have it basically humming after this. Now, increasingly, we're seeing our customers also come to us and say, hey, we really are depending on OpenSearch for a lot more than just analytics. We're actually running our business on this. We have dashboards that our customers use. We have searches that are powered by OpenSearch that power our website. And we can't afford any downtime. Now, in a single cluster, no matter how good that cluster is, it depends on all of the environment that it's running in. And so there's only so much you can do in terms of providing availability with a single cluster. Sometimes you just need more than one cluster. For example, with 3 nines or 3.5 nines, which is pretty good, you might actually see a few hours of downtime during the year. So what our customers have been doing is actually running multiple clusters to get better availability, to deal with disaster scenarios, protect themselves against disasters, as well as bringing data closer to their users so they can lower the latency for their access. The challenge has been keeping these clusters synchronized. They've been doing it manually, and it's hard. These things can get out of sync, and then it's very hard to kind of get them back to where they need to be. So recently, on the managed service in Elasticsearch 7.10, and in OpenSearch open source, we released cross-cluster replication. Provides high availability, disaster recovery, and data proximity for your applications. It's coming soon to the managed service in December 2021. It provides active passive replication for your clusters, both cross-account and cross-region support. And it gives you sequential consistency. So that way, when you query your data, you get a consistent view of your data. And the lag on your followers is less than a single minute. So the way it works here is that you have a leader domain or a leader cluster, and a follower domain or a follower cluster. And the follower cluster basically initiates replication of individual indexes on the leader, and then pulls the data changes continually to make the copy. The leader cluster can accept both reads and writes, indexes and queries, and the follower cluster only accepts queries, responses. And that way these things stay in sync. And because you can do replication at the level of a single index, you can set up all kinds of granular configurations. So, for example, one topology that you can set up is where you actually share the load of both reads and writes across 2 different domains or 2 different clusters that may be geographically replicated. In this case, the leader for index A will be domain A, and the follower for index A or index A prime is going to be domain B, and vice versa for index B. And so what you end up having is sort of a balanced ratio of reads and writes on both clusters, but you still get the properties that you're looking for, which is around availability and disaster tolerance and so on. Another common topology we see is one-to-many, where there's a single cluster where you're doing all your writes. In this case, the cluster is sitting in the US East 1 region of the globe. And then the replication is actually happening, the data changes are happening and getting propagated across the globe to the Pacific, to Asia, to Europe. And then the applications that are local to those areas are then using those search clusters to be able to serve the needs of their users. And the latencies get much, much shorter and faster. All right, so that was about cost at scale. Now I want to switch gears and talk about the great new algorithms and techniques that we've added in to do machine learning in OpenSearch. And we've actually released these things in open source that you can use today. So OpenSearch has a number of different use cases and workloads, but increasingly we're seeing customers coupling machine learning with all of their workloads for all their use cases. For example, if you had time series use cases, what they want to do is they want to do fraud detection and intrusion detection and monitor system health. And to be able to do this well programmatically is hard because the scenarios can change quickly. The number of signals that you have is kind of exploding. And so what they're doing is they're actually using automated anomaly detection to go and actually identify these and solve these use cases. Similarly for search, often search is used to go and find things that are similar. So to do things like collaborative filtering, to do product recommendations, personalization, and image search. And here, what they want to be able to do is find things that are very close or similar to the things that people are looking for. So one of the things that we added is k-nearest neighbor search in OpenSearch. This is very simple. You model all of your documents or your products or your images as a single vector in high dimensional space, multi-dimensional space. And when you're doing your searches, you look for the nearest neighbors in that high dimensional space. Now, doing this out of the box, without any special functionality, can take a long time. Either you're moving the data in and out of OpenSearch, or you're scanning through lots of data, and it can take minutes per query. Well, we've actually embedded k-nearest neighbors and the most leading edge algorithms of k-nearest neighbors inside the query engine itself, and it distributes across the cluster. So now, not only can you ingest in real time, but you can also query in almost near real time for your nearest neighbors. And the way you can kind of parameterize these queries is by changing the distance function, and we have a number of distance functions that you can try out. As an example, Novartis is actually using k-nearest neighbors to power their procurement system for their research scientists. They're trying to actually find equipment that they can use for their research. They're looking through 2 million different items with different vendors, prices, and properties. And with k-nearest neighbor search, they can very quickly get to the items that they need. Similar customers to Novartis, for example, have been using it for things like music recommendations, image search, and so on. And they've been able to bring down their latencies from minutes to literally less than a second. Another cool feature that we have that's embedded and integrated with OpenSearch is anomaly detection, especially for time series data. Now you can imagine if you have all kinds of applications running in the cloud, they have distributed architectures, microservice style architectures, or if you have applications running on-prem or on the edge, you have all of these sensors and their data sort of kind of coming in to you. You want to know where to look. You might have hundreds, if not thousands, of streams coming at you. Well, anomaly detection here comes to save the day. Our anomaly detection routines are performant at scale. You basically turn them on, and they run through your streaming data and tell you when something interesting is happening. It's super easy to use. You don't have to know anything about machine learning. And the algorithms that the techniques that we're using, these algorithms were actually developed in-house here at Amazon. And it's based on a model, a machine learning model called a random cut forest. And I'll kind of dig deep and explain to you how that works in a few minutes. But before I get there, let me tell you about Mobilewalla. They have a website where, they have a service, and what they were trying to do is they were trying to use what they are doing actually is they're using anomaly detection for detecting unauthorized access to their S3 buckets. So how does this all work? Well, the first thing you need to do is you need to figure out a way to actually summarize your data so you know what's normal and what's unusual. And anomaly detection has been around for ages, but this is the first time where people have been really wanting to do anomaly detection at scale and for streaming data. And so we needed to come up with a new summarization technique. And so we did. It starts with a random cut tree. So imagine, for example, you're tracking both CPU load and memory pressure. CPU load on the x-axis and memory pressure on the y-axis. And these points represent data points that have come in. A random cut tree is a tree that basically organizes these points in a binary tree. But the binary tree is built by first making random cuts in this 2D space. What we do is we create a bounding box for all of your points. And then we randomly cut along one of the two dimensions weighted by the size of the range for each of these dimensions. So in this case, the CPU load has a wider range, so it's likely that we're going to cut along the CPU load dimension. So this is the root of your tree, if you will. Then we recurse, looking at the right-hand side over here. In this case, the y-axis is longer than the x-axis, so you're likely to cut along the y-axis. And what you'll see is, these points that are sort of outliers up and to the right over there, it's going to, no matter how you kind of randomly cut, they're likely to be at the top or closer to the top or the root of the tree. And you keep recursing and splitting until basically this entire tree is formed and each point is isolated by these cuts. Okay. Now, this technique does give you a random cut tree, but if you're going over a huge, very long stream, you're going to end up with lots and lots of data, so your tree is going to get very big. And it might turn out that you end up with some unlucky cuts, in which case you're not going to really isolate all of the anomalies the way you'd like, right? Because we are building this randomly. Okay. So instead of building a single tree, the modification to kind of deal with those issues is to build many different trees, okay, each one with slightly different random cuts, and to build those trees on a random sample of the data. And that way, as the stream is coming by, you keep a small sample of the data, and you keep around 100 to 1,000 trees here. And the cool thing about this data structure, or what we call a summary structure, is that you can add and delete individual points as new points coming in, and it doesn't require you to recompute all the trees. You can just make small local modifications so that as data is coming in, you can very quickly adjust it, and those trees still have the same properties as you remove and add points, making it really, really effective for streaming applications. Now, to figure out what's an anomaly, you basically look at the tree, and when you try to add a new point to these trees, you check to see how much the tree changes, how much the depth of the tree changes. So if it turns out that something is added to the root or near the root, it's going to change the depth of a large portion of the tree, and so you're going to have a high anomaly score. Here's an example of a tree that we built with 6 points with CPU and memory, and you'll see the anomaly 70 and 90 actually shows up at the top. Okay. So this is the basic mechanism for building a summary structure, building a model over your stream, and then looking for anomalies. We released this in April 2020. We actually embedded it in OpenSearch, and we released it in 2020, so you could actually set up a detector per index, and you could you could detect anomalies for multiple dimensions, up to 5 dimensions. And it worked really well. We had a number of customers use it to identify when they had unusual increases in error rates of their distributed systems, when they saw unusual downloads or unusual activity in their systems, unusual spikes in I/O and CPU usage, network and traffic patterns, so that they could figure out where problems were or figure out where intrusions are coming to happen. But they looked at it and they said that they wanted more. Because, see, with this approach, what you have is that you have a single index, and if and you have a single stream that's coming in, it's often the case that sometimes you want to actually break up the stream into multiple tinier streams or smaller streams. For example, if you have a distributed system with multiple hosts, the hosts may be coming and going into your system. You don't want to constantly build an index per host. And the variations per host may vary. Some hosts might have fewer error counts, and some other hosts might have much larger error counts. And so what ends up happening is the ones that have fewer error counts will get swallowed from the hosts that have larger error counts, and you want to be able to separate that out. So we released high cardinality anomaly detection last year right around reInvent, where you could specify the substreams or the entities through a group by category. So in this case, host ID would be the entity, and you could scale to about 1,000 unique entities. And again, this worked really well until customers came back to us and said, no, it's not just host and error count, but we really want even more fine-grained, anomaly detection. And so just recently in OpenSearch 1.1, which we released already in the open source, we have even higher cardinality anomaly detection based on a modification of the random cut forest algorithm that allows and supports over 1 million entities, more than 1 million entities. You can actually specify additional group by categories. So in this case, you might group by host and error type and look at anomalies in the error counts per error type, for example. And you can basically scale as much as you need now with the new techniques that we've released. And again, this is coming soon to the managed service in December. How does this work? Well, we made a very simple trade-off. If you look at the random cut force model for every detector, the average memory size is about 8 megabytes. And if you have millions and millions of entities, it wasn't going to scale. So we had to drop and we had to compress the summary structure as much as we could. And we implemented a number of improvements on how we adjust the bounding boxes, how we share the tree data structures across different entities, how we represent those trees, how we compress the individual values in those trees. And these all work in unison to bring down the model size. Now, it also makes it harder to actually update the models periodically, but that's okay, because the stream might be coming in at like 10 or 12,000 events per second, but individual entities in that stream aren't going to be coming that frequently. They're going to be coming in like maybe once every minute or every 5 minutes. And so this trade-off actually made a lot of sense for us to be able to scale the anomaly detection feature that we have. Now, all of this wonderful technology first went into open source. It went into OpenSearch open source before it's coming to the managed service. And this is what you can expect going forward from us as well. So let's talk about the road ahead. We are now the stewards of OpenSearch and the core engine itself. And so before, we had to kind of work on the periphery of the core engine. Now we can actually start making modifications to the core engine to provide even better availability and resiliency and performance and cost improvements. You've already seen us implement cross-cluster replication. It's coming soon on the managed service for OpenSearch 1.1, but you're also going to see index level throttling. You're going to see techniques for doing skew avoidance or better load balancing during failures. We're going to provide support for Lucene 8.9 that gives you better performance. We talked about RCF 2.0, and we're actually also introducing a brand new distance metric in KNN to make it more memory efficient to be able to do your nearest neighbor searches. We're also improving the costs for our storage systems. We've also invested deeply and heavily into observability. We recently launched an open distro for Elasticsearch 1.12, which was part of Elasticsearch 7.9, which included Elasticsearch 7.9. We released OpenSearch Trace Analytics. What this does is it gives you an overview of your distributed system and the request and response patterns that are in your distributed system. It tells you, where things are going too slow, where the microservice dependencies are, and where you might be running into problems. And this is all based on an open standard called OpenTelemetry that is getting a lot of traction today, and a lot of customers and institutions are starting to adopt this standard. We also released with Data Prepper the ability to store and normalize these traces into OpenSearch. And going forward, we're going to be allowing you to normalize the traces along with logs and metric data in Data Prepper. And then finally, we're working on, out of the box, single pane of glass visualizations and dashboards for various specific vertical use cases. So you can get started very quickly as soon as the logs start coming in. You can start getting insights and start playing with the data that you have. All right, to recap, the Amazon OpenSearch service is the same great service that you're used to. It provides the same flexibility based on OpenSearch and the OpenSearch project. OpenSearch is fully open source. It's Apache v2 licensed, backward compatible, and gives you, provides the property of no lock-in. You can run it anywhere you want, on-prem, other clouds, and in particular on the OpenSearch service. We're also innovating and investing in cutting-edge features that we released to open source and on the managed service. We went through a number of them today, and more. There are more to come. So the innovation that you're used to, the pace of innovation that you're used to, you can continue to expect in OpenSearch. So thank you so much for listening, and let me pass it on to Wei Zhu now. He's the staff software engineer of observability at Pinterest, and he can tell you about their journey with OpenSearch and their product. Thank you.
Thank you, Maihao. This is Wei. I'm the software engineer in observability team at Pinterest. Today, I'm going to talk about log search at Pinterest. We store logs, main application exception logs, emitted from several hundreds of services in AWS managed OpenSearch clusters. Logs are key in reducing the mean time to resolution for incidents. Our 1,000 engineers use OpenSearch dashboard every day to visualize the logs in near real time, which is a main tool for root cause analysis. We also monitor performance stats and detect degradation using XSLog and mobile client logs. In order to have a holistic view of the services from both logs and metrics point of view, we generate the metrics from logs by calling OpenSearch API. Those metrics are ingested to Pinterest metrics pipeline and used for generic alerting and automated canary analysis. Before 2017, we used a self-hosted Elasticsearch cluster that resulted in huge operational overhead. Then from 2017 to 2020, we switched to a third-party SaaS vendor, but it cost too much, and the query performance was poor. It also uses a proprietary query language. The learning curve is simply too high for our users. In early 2020, we migrated all the logs to AWS OpenSearch services. Today, we have 7 clusters, total of almost 200 nodes. We have 240 log streams, 12 billion daily records, and we ingest 6.6 terabytes daily volume. Meanwhile, we only need less than half engineer to keep the lights on. From this chart, you can see the tremendous growth for the past 18 months since we migrated to OpenSearch. Daily log volume had grown from a little over 1 terabyte a day to 6.6 terabytes. Number of daily records has grown from 2 billion to 12 billion. And we are ingesting logs from more than 240 services now, compared to less than 100 just 18 months ago. Now, let's talk about the log search architecture. At a high level, the infrastructure is composed of 4 tiers: collection, ingestion, storage, and visualization. The collection tier is responsible for collecting logs from the data sources and forwarding them to the ingestion layer. We use Singer to ship logs to Kafka. Singer is an open source project developed by Pinterest. It's a high-performance logging agent for uploading logs to Kafka. Singer runs as a standalone process on the service boxes. It monitors the log directory by listening to file system events and uploads data once it detects new data. Singer guarantees at least one-time delivery of log messages. It's similar to Firebeat. Logstash reads the log message from Kafka and ingests them to OpenSearch. In Logstash, we apply a set of plugins. Depending on the logs, different plugins are applied. Common ones are Grok plugin to parse the logs, Throttle plugin to throttle the logs, Mutate plugin to convert fields to desirable types and scrub sensitive information. Logstash instances are deployed to Kubernetes, which makes it easy to scale horizontally. We use AWS managed OpenSearch as a storage layer, which is responsible for indexing the logs and making them available for search. OpenSearch is fully managed services that makes it easy to deploy, scale, and upgrade. We choose OpenSearch for its simplicity in terms of management, scalability, and security. In order to support the growth of our log footprint, we choose to physically shard the log streams across multiple clusters and build tools for users to discover the logs in different clusters. We use OpenSearch dashboard to visualize and search logs stored in OpenSearch. We also develop a tool to generate metrics from logs. Those metrics are ingested into our observability metrics pipeline. They can be used in metrics dashboards, alerting, and automated canary analysis. In order to avoid the noisy neighbors effect, each service has its own isolated ingestion pipeline from Kafka topic, Logstash cluster to OpenSearch indices. We build tools allowing the service teams to provision Kafka topics and the Logstash clusters. All those operations can happen without involving the observability team. This significantly reduced operational burden for our team. To reduce the storage cost, we enabled AWS Ultrawarm on the clusters. Logs in Ultrawarm are cheaper to store, but slower to access. This is perfect for older logs since they are rarely accessed compared to the more recent logs. We store the logs in hot tier for 7 days and Ultrawarm tier for 30 days. We also recently enabled cold storage on the clusters. Cold storage decouples computer from storage, which results in more savings. For the logs which needs more than 30 days of retention, we store them in cold tier. Enabling Ultrawarm and cold storage not only saves us money, which is more than $500,000 a year, but also allows us to serve some other use cases which were not possible before. In such cases, we store the mobile performance log for 2 years. We also take advantage of the security feature OpenSearch provides. We enabled SIMO integration with Okta for dashboard access, which is a major improvement from the previous Cognito integration. It allows us to use existing identity provider to offer single sign-on for accessing logs on OpenSearch service domains. On top of SIMO, we are also using FGAC to control access at the index level. I will get into more details of the FGAC implementation when I'm sharing the Kubernetes console logs use case next. As you all know, in Kubernetes, debugging issues are very challenging, especially when the pods are running into issues during startup. If the pods fail to start up correctly or crash, the logs from containers are gone. Let's not forget about the highly distributed and dynamic nature of Kubernetes. In production, you will more than likely work with several machines, each having multiple containers that can crash at any time. It becomes very complicated to get the logs you are looking for. Besides, if the workload is running on a large number of pods, looking at the logs using Kubernetes control would be overwhelming, and it also adds a noticeable impact to the Kubernetes API. This is why we develop a logging solution for the Kubernetes standout and stand error logs. We already set up a logging pipeline to ingest the container's application log. It follows the same architecture described in the previous slides. The container logs on Kubernetes are written to the log file into var log inside the container, which is backed by a special container log volume accessible to Singer, our logging agent. To capture the console log, we have kubelets to create a symlink of the application console log collected by Docker into the existing logging pipeline. Singer is able to handle Docker container rotation as well as container restarts. When we added the capability for Singer to ingest some special values such as pod name, file path to the Kafka headers, that will help us to enrich the logs with necessary metadata. Logstash reads the file path from the Kafka header. The file path is composed of project, pod, and container name. And by reading that, Logstash knows the project which this log belongs to. It then can create daily indices for each project so that it's easier to scale and manage. Now let's talk about how we manage authentication and authorization. The logs are shared by projects. We already have the Rego policy set up to control Kubernetes resource based on the project. Rego is a high-level declarative language to describe open policy agent policies. We developed a cron job to read the Rego policies and set up the OpenSearch roles and permissions accordingly using OpenSearch API. With SIMO integration and OpenSearch FGAC capabilities, we are able to control access to the logs at a very fine-grained level. To recap the Kubernetes console log use case, logs are persistent in OpenSearch even after the pods are terminated. Current logs from 70 different workloads are ingested to OpenSearch. The whole process is fully automated. User will get the console logs automatically when the new workload is deployed to the Kubernetes. We use the same Rego policy file to control the Kubernetes resources and OpenSearch indices. No additional setup from users are needed to enable logs. Here are the key takeaways of using AWS Managed OpenSearch Services. With AWS Managed OpenSearch Services, it can scale easily to fit our use case. Again, low cost of maintenance with AWS Managed OpenSearch Service is a big advantage over other solutions. We only need less than half engineer to keep the lights on so that we can put resources to other observability areas. It has quite a big saving with R2 Warm and cold storage tier. Being able to save money is always a good thing. Last but not least, the advanced security feature can allow us to keep our data safe and secure. AWS OpenSearch has been a valuable partner for us, and we are looking forward to more exciting features from them. That concludes my part of the presentations. Thank you.
Thank you, Wei, for telling us about your journey with OpenSearch. And thank you, users, customers, and contributors for staying with us. And I'm super excited about the journey ahead.